Okay, in this video, we're going to start Chapter 2 of the chemistry textbook. Chapter 2 is on atoms, molecules, and ions. So what are atoms, molecules, and ions? But the chapter begins with sort of a history lesson, a two-part history lesson. So the first part is a history of atomic theory, right? So the theory that matter is made up of these really small building blocks called atoms. This hasn't always been the prevailing theory of matter. Not at all. So that's what we're going to talk about in this video. Okay, in the next video, the second part of this brief history lesson, we're going to look at how the modern understanding of the structure of the atom was developed. So not atomic theory itself, but in this case, we're talking about the discovery of the electron, the nucleus, the proton, the neutron, etc. Okay, but we're going to start with atomic theory. Okay, so again, atomic theory, the atomic theory of matter, of what matter is made of. The theory that all matter is made up of these really small building blocks called atoms. And as we talked about in Chapter 1, it's called atomic theory, but remember, a theory in terms of science is as close as you can get to a fact. Once you have a topic that is constantly being validated with multiple proven hypotheses by different scientists in different locations, different experiments that point to the truth of what this topic is stating, then it eventually becomes a theory. It's kind of like a universally highly accepted opinion is the way you can think about it. Okay, so it says, since ancient times, humans have pondered the nature of matter. Our modern ideas of the structure of matter began to take shape in the early 19th century with Dalton's atomic theory. We now know that all matter is made of atoms, molecules, and ions. All of chemistry is concerned in one way or another with these species. So atomic theory really started to gain momentum in the early 19th century, the early 1800s, late 1700s, with John Dalton. Okay, but before this time, the most universally accepted theory of matter was not based on these really small building blocks. Okay, so you had, in those times, you had Aristotle's theory that all matter was continuous, composed of four continuous elements: earth, air, fire, and water, that could always be divided into smaller, infinitely divisible pieces without reaching a smallest particle. Okay, so it says, in the 5th century BC, so well before the late 1700s, early 1800s, the Greek philosopher Democritus expressed the belief that all matter consists of very small indivisible particles, which he named atomos, meaning uncuttable or indivisible. Although Democritus's idea was not accepted by many of his contemporaries, notably Plato and Aristotle, somehow it endured. Experimental evidence from early scientific investigations provided support for the notion of atomism and gradually gave rise to the modern definitions of elements and compounds. In 1808, an English scientist and schoolteacher, John Dalton, formulated a precise definition of the indivisible building blocks of matter that we call atoms. So the question naturally arises, you've got this Democritus in the 5th century BC has this atom theory, but it doesn't gain traction. But with John Dalton in the early 1800s, late 1700s, it does. And it says here it's mainly because of experimental evidence. So you wonder what was the experimental evidence that allowed atomic theory to gain momentum over these other theories from Plato and Aristotle. Well, what we can think about is we're going to learn in Chapter 8, when we get into the details of the periodic table, in its history as well. That so at the time, so atomic theory gained traction, and then in the mid 1800s, late 1800s, they were discovering many more elements and sort of organizing and creating the periodic table. And at the time, what they were using to organize the periodic table was atomic mass. So they were able to, at that time, they had the technology to accurately measure masses that were extremely small, very, very precisely at the atom level, right? Which they weren't able to do in the 5th century BC. And so we can make an educated guess that, so they were measuring these masses of elements in the mid 1800s, late 1800s, but around the time of Dalton, the mid to late 1700s, maybe even a little bit before that as well, in the times at the end of Isaac Newton's life, just to give you some perspective, maybe they didn't have the technology quite yet to measure masses at the precision of atomic size. That would be like a nano size scale, but maybe they could measure masses at the precision of a micro scale, still really small. And so what we want to think about is, with the ability to measure masses that precisely, they could use this to precisely analyze mass relationships in chemical reactions. They could take some carbon and some oxygen, precisely measure the mass of each, then put them together in a chemical reaction. Okay, then one of those reactants would be fully used up with some left over for the other reactant, right? But so with that, they could get a sense of exactly how much mass was consumed to create this new product here of carbon and oxygen, this new gas. Because you had some of the carbon, some of the oxygen completely disappear and create this new gas, but they could measure how much mass was in this new gas, how much mass of carbon and oxygen, right? They could do this kind of mass analysis with chemical reactions very precisely. So let's keep that in mind. Okay, so Dalton's work marked the beginning of the modern era of chemistry. The hypotheses about the nature of matter on which Dalton's atomic theory is based can be summarized as follows. So what we can think about is that with Dalton and other scientists studying these chemical reactions, these mass relationships, certain principles became evident. And these principles pointed to the existence of these really tiny building blocks. Okay, and so let's go through these Dalton's hypotheses here, which might seem trivial to you watching this video, but remember, at the time, this was not trivial at all. Okay, so the first hypothesis is that elements are composed of extremely small particles called atoms. Okay, hypothesis 2, all atoms of a given element are identical, having the same size, mass, and chemical properties. The atoms of one element are different from the atoms of all other elements. So you've got these very small particles called atoms. That's like the building blocks of all matter. And they had a sense of, if they were dealing with a pure substance composed of just one type of building block. And so the only statement was that you've got these small building blocks called atoms that only differ based on the type of material you're dealing with. But if you have the same material, like pure gold, pure oxygen, pure hydrogen, then there's only one type of atom in that substance. The atoms do not differ. Okay, hypothesis 3, compounds are composed of atoms of more than one element. In any compound, the ratio of the numbers of atoms of any two of the elements present is either an integer or a simple fraction. Okay, so they had a sense that there were substances that had more than one type of atom mixed in, because they could do experiments like take some carbon, take some oxygen, put them together, add some heat, and then the carbon and oxygen sort of disappeared. Or maybe you could think about, it would be more intuitive, you have two solids that come together, two different types of solid elements, mix them together, add some heat, they combine and just disappear, just become this one substance. So they were surmising, well, there must be in this new substance more than one type of atom. And they call these compounds. Okay, and in any compound, the ratio of the numbers of atoms of any two of the elements present is either an integer or a simple fraction. So yeah, you could just think about where a hypothesis like this would come from is these mass relationships. You analyze the mass that's consumed to make some compound, it's always these simple ratios. Okay, but then furthermore, with hypothesis 4, it says a chemical reaction involves only the separation, combination, or rearrangement of atoms. It does not result in their creation or destruction. Right? So when they were analyzing these mass relationships, they weren't seeing any evidence of certain types of elements sort of disappearing and transforming into another type of element. You could always track the masses of different elements, no matter what kind of compound or reaction they were put into. Okay, now with hypothesis 3, we want to think about, so when they would combine these elements in reactions, it was really more than just when they would compare the ratios of the elements, they would get these integer values in the ratios. It was also, they were getting simple fractions. So you can have a ratio of integers. We can say 3,213 to 7,812. That's a ratio of integers. But what they were seeing was that it would always come out to be, it would simplify down to a relatively simple ratio, 7 to 2, 5 to 3, etc. Now, it's not like we know today that there's certain molecules that have thousands of like carbon atoms and hydrogen atoms in the same chain. Okay, but in most cases, it really comes down to these simple fractions, right? You like the atoms combine to form CO2 or CO, H2O2, and this was just evidence of these atoms simply rearranging themselves in chemical reactions. The different types of atoms weren't being created or destroyed. They were always conserved. And then when you had a chemical reaction and combined or separated these types of substances, these elements, the atoms were just rearranging themselves. So you always end up with these, when you track the mass relationships, it was these simple ratios of integers, right? So you've got this atom of element X, this atom of element Y. You combine them together and get a relatively simple combination here. With 2 for each of these molecules here, you have 2 atoms of element X and 1 atom of element Y. Now, does that mean from a mass perspective, if you did this reaction and tracked the mass used of this element and the mass used of this element, you would get a 2-to-1 ratio? Well, no, because you can see these two elements are, the gray elements are smaller and lighter than the red elements, but you're still going to, when you track the mass ratios, you're still going to get some simple ratio. Okay, but again, they also, at the time, they could measure masses accurately, so they did have a sense of, we can think about how they did have a sense of, okay, well, this is a lighter element than this. So maybe they could apply correction factors and figure out, okay, well, it could be the case that if we do think about these building blocks, then the mass ratios are telling us that for every 2 of these building blocks, you have 1 of these building blocks used to create this product here. Okay, so it says, Dalton's concept of an atom was far more detailed and specific than Democritus's, and backed by more experimental evidence. The second hypothesis states that atoms of one element are different from atoms of all other elements. Dalton made no attempt to describe the structure or composition of atoms, right? That's what we're going to do in the next video. He had no idea what an atom is really like, but he did realize that the different properties shown by elements, such as hydrogen and oxygen, can be explained by assuming that hydrogen atoms are not the same as oxygen atoms. Yeah. Okay, so now to finish off this history lesson here, we're going to talk about how Dalton's hypotheses were in line with, matched up with, some other laws of matter that were stated at the time. So the law of definite proportions, or what's also known as the law of constant composition, the law of multiple proportions, and the law of conservation of mass. All right, now keep in mind these laws here were stated in this time period, in this late 1700s, early 1800s time period. So this still is really more of a history lesson. However, it's not like these laws aren't really important today. I mean, the law of conservation of mass, we still do physics and chemistry with that law as one of the foundations. But just keep in mind, we're still doing sort of a history lesson here. This is still that late 1700s, early 1800s period. So the third hypothesis by Dalton suggests that to form a certain compound, we need not only atoms of the right kinds of elements, but specific numbers of these atoms as well. This idea is an extension of a law published in 1799 by Joseph Proust, a French chemist. So Proust's law of definite proportions, also known as the law of constant composition, states that different samples of the same compound always contain its constituent elements in the same proportion by mass. So yeah, notice it by mass, right? They're analyzing these mass relationships in these chemical reactions. They don't know about the atom yet. They're just seeing what the masses are doing to create these different compounds. Okay, so thus, if we were to analyze samples of carbon dioxide gas obtained from different sources, we would find in each sample the same ratio by mass of carbon to oxygen. It stands to reason then that if the ratio of the masses of different elements in a given compound is fixed, the ratio of the atoms of these elements in the compound also must be constant. Right, so they're saying if you've got the same substance, in particular a compound in this case, with more than one atom, but the substance is obtained from completely different sources, seemingly as far as where the substances are coming from, where you found them, how they were created, is completely different, but it is the same substance. Then no matter what, if you compare the ratios of the masses, the ratio of the masses of the different types of elements in the compounds, you're going to get the exact same ratios for these substances coming from these different sources, the ratios of the masses. And so that's why it's saying it stands to reason that if you look at this from the perspective of atomic theory, this must be pointing to the ratios of the atoms of those elements being the same. And we know this is true. The whole idea here is it's like you can't, we know that you couldn't have a glass of water or a container, a vessel of water, and pump high pressure oxygen gas into the water and think about the idea of, okay, we're increasing the concentration of the oxygen in the water. So now the water is, instead of being H2O, it's H2O2. So it's a higher concentration water. We know that doesn't make any sense. Water is H2O. If you change any of those atoms, you don't have water anymore. If you're dealing with water, no matter what, you're going to have 2 parts hydrogen to 1 part oxygen, no matter what. No matter what the circumstance. It doesn't matter if the water is hot, cold, what state it's in, where it came from, doesn't matter. Water is 2 parts hydrogen to 1 part oxygen. Okay, now Dalton's third hypothesis supports another important law, the law of multiple proportions. So I believe Dalton stated this law in 1803. Okay, so according to the law, if 2 elements can combine to form more than one compound, the masses of one element that combine with a fixed mass of the other element are in ratios of small whole numbers. So here what was being analyzed was so that they could see that you could combine like carbon and oxygen to create one type of compound like carbon monoxide, then you could combine it in another way to create something like carbon dioxide. You could create different substances with the same elements, with the same mixtures of elements. And so what they're doing here is they're comparing, well, okay, how does when we create from carbon and oxygen, when we create carbon monoxide and we see how much carbon is used and oxygen is used, how does that compare to the amount of carbon and oxygen used to create carbon dioxide? They didn't know it was carbon dioxide. They just knew it was a different substance. Okay, and what they found was that when you compare the different masses, if it was a carbon dioxide to carbon monoxide, then they were seeing that, okay, it's the same amount of carbon is being used up for both, but it's different amounts of oxygen. But when they compared the ratios of the mass of the oxygen used to create this carbon dioxide substance, which they didn't know what it was, to the carbon monoxide substance, which they didn't know what it was, the ratios of the oxygens were these small whole numbers. And that makes sense, right? This is pointing to it, the validation of atomic theory. Okay, so Dalton's third hypothesis explains the law of multiple proportions quite simply. Different compounds made up of the same elements differ in the number of atoms of each kind that combine. Yeah, exactly. H2O, H2O2. For example, carbon forms two stable compounds with oxygen, namely carbon monoxide and carbon dioxide. Modern measurement techniques indicate that one atom of carbon combines with one atom of oxygen and carbon monoxide, and with two atoms of oxygen and carbon dioxide. Thus, the ratio of oxygen and carbon monoxide to oxygen and carbon dioxide is 1 to 2. Now, the mass ratios would be different than 1 to 2, but still, the mass ratios would still come out to these small whole numbers. This result is consistent with the law of multiple proportions, which again, I believe is Dalton created this law in 1803. Okay, now Dalton's fourth hypothesis is another way of stating the law of conservation of mass, which is that matter can be neither created nor destroyed. Because matter is made of atoms that are unchanged in a chemical reaction, it follows that mass must be conserved as well. Dalton's brilliant insight into the nature of matter was the main stimulus for the rapid progress of chemistry during the 19th century. Yeah, so I mean, we can think about how you could still have the law of conservation of mass apply, but with atoms for some reason exchanging protons or something, right? But in that case, I guess chemistry would sort of be redefined to where the main characteristic of elements wouldn't be the number of protons in the nucleus. Okay, but it's still powerful to state this theory of the law of conservation of mass. It didn't sound like with Aristotle's theory of this continuous matter that there was really a requirement that mass was conserved. You could have mass disappear or appear, right? But we know that that's not the case. This law of conservation of mass is very important in physics and chemistry, as well as the law of conservation of energy. You can always track where the mass went and where the energy went in any system, kind of like an accounting book with money. That's the law of conservation of mass is what balancing chemical equations is all about. In any chemical reaction, chemical equation, the masses need to balance. The masses of the atoms. You have to be able to. You're tracking where the mass went. You're doing an accounting balance on the elements, the masses. That's exactly what balancing chemical equations is all about. It's centered on this law of conservation of mass.